This is Rudy Garcia, and I will be talking about how carbon dioxide outgassing constrains the habitability of rocky planets after their host M dwarfs pre-main sequence phase. So that's a real mouthful, but there are three moving parts to this project. One is carbon dioxide outgassing. We're going to be talking about the habitability of rocky planets, and key is that we're going to be talking about the pre-main sequence phase of M dwarfs. So the motivation for this project is that we've detected all of these rocky planets that are in the habitable zone around M dwarfs. But because of how M dwarf habitable zones change with time, they move inwards. We think that these planets probably experienced a significant runaway greenhouse effect in the past. So you can see here that as the inner edge of the habitable zone of TRAPPIST-1 moves inwards, eventually it sort of encompasses TRAPPIST-1e. But up until this sort of white curve and red curve intersect, TRAPPIST-1e is actually interior to the habitable zone and receiving so much stellar radiation that it's likely in a runaway greenhouse phase. So it's losing lots of water and it might be uninhabitable at that point. So the question here is, how does this period of sort of runaway greenhouse effect influence the potential habitability of the planet now? So what's key during this process, during the runaway greenhouse phase, is how much carbon dioxide was outgassed during the pre-main sequence phase. See, while the planet is losing water, it's also outgassing carbon dioxide from its interior. And eventually, when the planet enters the habitable zone, we have to consider how much carbon dioxide is in the atmosphere and what the extent of greenhouse warming is due to that carbon dioxide. You see, if you outgas too much carbon dioxide, you end up with a thick greenhouse atmosphere that results in liquid water being unstable. Whereas if you don't outgas a lot of carbon dioxide during this pre-main sequence phase, you end up with a sort of more tenuous atmosphere where liquid water is stable. So the key thing that we're looking at here is how much carbon dioxide is outgassed during this phase. So how do we look at this? We use vPlanet, which simulates the evolution of planets over time. So specifically, we use vPlanet to simulate the thermal evolution of the planet, its atmospheric evolution, and the evolution of the host star, which sets how much water gets lost to the atmosphere. A lot of the details are here in the bullet points on the right, but really what's going on is we're just tracking how heat leaves the interior of the planet through volcanism, and how those volcanoes, represented by these purple arrows, spit water and carbon dioxide into the atmosphere of the planet. And then, of course, water might leave the atmosphere into space during the pre-main sequence phase. And if liquid water is stable, carbon dioxide might leave the atmosphere and be weathered to the crust. So we use this model to simulate TRAPPIST-1e. We assumed an Earth-like composition and a stagnant lid tectonic regime. And here are our results. Our model runs fast, so we can explore parameter space with this. We varied on the x-axis what fraction of volcanism actually results in carbon dioxide and water reaching the atmosphere rather than getting trapped in the crust. And on the y-axis, we varied how much carbon dioxide TRAPPIST-1e formed with. And you can see here that water is liquid on TRAPPIST-1e only if the amount of carbon dioxide that reaches the atmosphere is limited. So what's happening here is these sort of black squares where there is no liquid water on the surface of TRAPPIST-1e. The reason there's no liquid water is because so much carbon dioxide has outgassed that we have a thick greenhouse atmosphere, and it results in liquid water not being stable. So this is really key. The goal of this project is to sort of communicate that this is a really key point, this sort of outgassing during the pre-main sequence phase. So in conclusion, in order for a planet to become habitable after the host star's pre-main sequence phase, it must have low amounts of carbon dioxide in its atmosphere, which can be accomplished by forming with low amounts of carbon dioxide or having a low eruption efficiency. And more specifically, TRAPPIST-1e's potential for habitability is constrained by the need for either an initial carbon dioxide budget much less than Venus and Earth's, or an eruption efficiency much less than Venus and Earth's. Thanks.